Let's have a look at what SME Lookup Table is. SME Lookup Table is a 512-bit architectural register accessed as ZT0. And this is a 512-bit register that can hold 512 bits of data. Since it is being accessed as a lookup table feature, the feature enables to make 16 entries in the lookup table. The ZT0 constitutes 16 entries of lookup table. Each entry is 32-bit wide. 512-bit divided by 32 bits gives you 16 entries. It is not mandatory for every 32-bit entry to have 32-bit wide data. The 32-bit entry can be a 8-bit element or a 16-bit element or a 32-bit element. Maximum it can hold is a 32-bit element. Now that we have 16 entries, we need 4-bit indexing to index one of the entries in the 16 entry table. Architecture in SME permits to use 2-bit indexes as well as 4-bit indexes. So indices can be 2-bit or 4-bit. With a 2-bit index, you can access 2 to the power 2, that is 4 entries only. That is, though ZT0 will be having up to 16 entries, you can access only the first 4 entries using the 2-bit index. Whereas using the 4-bit index, you can access the complete 16 entries. ZT0 can be loaded from the memory and stored into the memory. The advantage of ZT0 is once you have the data loaded into the ZT0 and is available, you can use instructions to access the data from ZT0 in a format, or you can choose which entry from ZT0 should be accessed and loaded into the register in different ways. Let's have an example on that. Here we are just showing how we can load the data from memory into ZT0 and store back the contents of ZT0 into the memory using the regular load and store instruction. There is a load LDR ZT0 and STR ZT0 that can be used with address pointed in one of the general purpose registers. The lookup table has exclusive instructions to read the lookup table. LUTI instruction can be used to read contents from the lookup table. And LUTI2 indicates that you are using 2-bit index, which means you can access only one of the 4 entries, that is one of the first 4 entries in the lookup table, and load it into a destination vector register. That is, read contents from ZT0 depending upon the indexing with either 2-bit or 4-bit indexing. You can access one of the entries, and the corresponding entry can be copied into a vector register. Okay, here is an example. Let's see, we have ZT0, which means you are reading the data from ZT0 using the lookup table instruction. You are using a 2-bit index. That is what this 2 indicates. What does the Z5.h and Z02 indicate? Let's look into the details. The Z0 is one of the source registers where the indexing is stored. The 0 indicates that we use a segment 0, and it is a 128-bit wide register. We are considering this particular implementation is 128-bit wide. The 2 here indicates that use segment 2, and the segment of each size is determined by the element size and the indexing that we use. So based on that, we can derive what is the segment size. This segment size is 16-bit, and each index will use 2 bits because it is a 2-bit indexing. And using these indexing from Z0, one of the entries from ZT0, since we are using 2-bit indexes, you can only index one of the entries within the first 4 entries, and each entry is 32-bit wide. One of these entries is chosen and loaded into the destination register. The destination register used here is Z5. And here a .h represents that we are accessing 16-bit element. So this is telling us, though the entry in ZT0 is 32-bit wide, we are going to load only the lower 16 bits. access only 16 bits from the lookup table is determined by this hedge, and that gets loaded into the first 16 bits. So the first 16 bits in the Z5 register gets loaded by the indexing used in Z0 register. It's a 2-bit indexing. It could point to any of the entries here. That particular entry is loaded. Say it is indexing is 01, then entry 1 is loaded into the 16 bits of entry 1. The lower 16 bits of entry 1 is loaded into bit 15 down to 0 in Z5 register. Similarly, the next 16 bits will be second element. This is indexed by IDX1, which is part of Z0. Thereby, we can construct the data that we need in Z5 using the lookup table, ZT0, and then use it for further processing. That is the lookup table feature with an example. The another key feature of SME is predicate as counter. Unlike the regular bit mask predication, the SME uses a encoding for predicate registers. The encoding mechanism helps identify how many number of consecutive elements are active in a particular fragment of data process. So usually we use predicate registers to indicate which data fields are active in a particular transaction, which data fields are inactive in a particular transaction, like in SVE. However, in SME, we are using a different mechanism called predicate as counter, in which we use encoded value in the predicate register. What this encoded value indicate is, they basically give us count of number of elements starting from element 0 in a particular transaction, how many elements are active, and after that many elements, we can consider the remaining elements as inactive. The encoding can be used in both the ways to indicate the first set of elements are active and the rest of the elements are inactive, or we can also encode it to indicate the first set of elements, the first set of consecutive elements are inactive and the rest is active. So with the remaining elements of inactive or vice versa. That is, you can also tell the first set of elements in this particular data process is inactive, that is encoded in the predicate register as predicate as counter. And bit 15 down to 0 of predicator is used for the predicate as counter encoding. How we will use it, we'll look into more examples in the next module, SME instruction set module. For now, this is just to explain the concept. Okay, so predicate as counter is normally generated. All the encodings can be generated and used with the while instruction. Along with example, we'll see in greater detail in the next module, instruction set module. Before we wind up, here is a summary of what we went through. We started off with what SME architecture is all about. We introduced you with all the SME architectural features. Some of the key features we went in with greater detail. The objective was to introduce you all attending the training to get through the SME architectural key features like streaming SVE mode and ZDA storage and how it can be used in the application, and how the data can be accessed in the ZDA storage as a vector access, as a tile, as a horizontal slice, vertical slice, etc. for different element sizes. And we also covered the SME lookup table and SME predicate as counter mechanism. This was the objective, and I believe we covered all of the objectives. Thank you for attending this training. The follow-up of this would be the instruction set module. Let's sync up on the instruction set module again. Thank you.